Okay. Homebrew transceiver. This is a 40 meter CW transceiver, and it's not finished. It's still being worked on. But I thought I would just kind of bring you up to where I am. I started this about September of last year. And I think at the time, I brought some pictures in of a front panel. But anyway, let's go to the next screen. First thing about building stuff, an item, is to have a realistic goal. It's just like any other project. Software is particularly bad with this. You get feature creep. The features, you want all these features in, and there's more features than either you have time for, the ability for, or maybe the money. But I was in the same situation, and I have, I guess you'd call an Elmer or a mentor in Australia, a VK3AQZ, that is actually ahead of me building a all-band unit. And he's an RF engineer, and he's been kind of helping me along. But he suggested just go for one band initially, make it easy. Low power, in this case, I think it's 15 watts. CW only. Why? Because I only do CW. This is, for me. So don't duplicate what you have. And that may sound rather odd, but I do have an IC7200 all-band 100-watt rig. So why would I build a 100-watt CW or all-band rig and play one against the other? I'm going to use this one or I'm going to use this one. So I decided that this would be semi-portable, not big, not high power, something that you could certainly not carry the mountaintop, but on a field day or a campsite, you would work just fine. Whereas the 7200, which really didn't sell well in Japan, is kind of a squat thing with steel handles, and it weighs a ton. I mean, it's built like a battleship, and you don't carry that thing very far. The other thing I wanted was a DDS VFO. Many, many, many years ago, I tried to make an analog VFO, and I could never stabilize it. I mean, it would just whoop, whoop, whoop all over the place. So with today's technology, either DDS or synthesizer type chip is the real, it's an easy out. A kit RFPA, the RF power amp, they can be tricky in getting them so that they don't have tons of spurious emissions, or they don't burn up the board and do other kinds of nasty things. And unless you have some pretty high-end test equipment, they're pretty hard to make, just by yourself. So I opted for a 15-watt kit from a company called Mini Kits in Australia. And it's quite reasonable. And there's some surface mount, and it uses RF type MOSFETs, which are quite good. Lastly, document everything. Document before you start, when you're working, after you finish the day session, bring your documentation up to date. Because I will guarantee you, a week afterwards, you'll never remember what you did. So I've got right now a folder that is 120 pages. It's a clear folder, it's 120 pages, I think, is chock full of schematics and diagrams. And I keep that up pretty religiously. So these are just some tips to start off with. Basically, this is the block diagram. And it's not, when you think low power, one band CW transceiver, this may seem like overkill. But it's really pretty simple. It's a single conversion. It's not double conversion or triple conversion. It's single conversion. In other words, the architecture is very similar to the days of Drake with the TX4 and TR4s, or the RX4s. Single, in my case, I'm using 8.3 megahertz IF, whereas they use 9. Even the Elecraft K2 is one conversion at 4 megs. But basically, you have low pass filter, an RFPA, which this is both receive and transmit. For receive, there's some pin diodes that switch bypass it. Come up through a bandpass filter. And at this point, you make the switch between receive and transmit. For receive, with an attenuator, RF amp, a simple 1496 mixer. This is a real old style double balance mixer. It's not a diode type balance mixer. It's a Gilbert cell. And then the crystal filter, a single IF amp, an AD603. That's actually a video amp. It has about 40 decibels of gain. See, has good AGC on it. Surface mount. So from there, we go into another product detector, which is the 1496 again. And then into the DSP filter, like I made before. I bought that third small board. And then into the mute circuit AF amp. Here's the DDS-VFO, and it feeds a hybrid splitter, so it either can feed the mixer or the RF amp. And the DDS-VFO, which we'll see in a minute, is interesting in that it has an RIT function that can actually go plus and minus 10 megahertz. So, and it operates very, very fast. So what you can do is, for transmit, you just engage the RIT, and the offset is your IF frequency. So, for example, I would have to add 7 megahertz, add the 8.3, and it put out about 15 megahertz to drive the receive chain. But for transmit, turn on the RIT, it goes back down to 7 megahertz, and I can just run it right straight through. If it was sideband, then I would have to run it through another mixer and all kinds of garbage. But for CW, it's pretty straightforward. For the BFO, and you'll see this also, this is very interesting. Everybody remembers Hans, QRP Labs. This is one of his products. It's called a programmable crystal. And I think it was 2,500 yen. Super cheap, as usual, but it's neat. And we'll see that. So that's basically what it amounts to. And we'll see more as we go along. If there's any questions, feel free to ask. Now, this is the DDS that I use. It's from a guy in Nevada, N3ZI. And it's, I think it was about 4,000 or 5,000 yen. Well, this is the PIC controller, and then there's the DDS chip, and then the LCD, and the mechanical encoder that comes with it as a set. And it was originally intended to be a VFO replacement for tube-style transmitters. So, from a solid-state transceiver feature point of view, it's a little weak. You know, it does have A and B switch, and you can change the step size. And what you can't do is, well, it has it, you can do a split, but you can't force one memory into another. Like for a split operation, you would like to force A into B immediately when you go into split, so that you're sitting one on top of each other, and then you can move it B away. This, you have to search out B and move it yourself. So it's a little bit on the rough side. Also, the DDS chip is not really super top of the line. It's moderately expensive. It's so-so. There are better ones. This is only, I think it's 12 bits. The better one's 14, 16 bits, but a little bit of money. But that may be the next project. So the good thing about it is it'll go down to 1 hertz steps. A lot of them are only 10 hertz. And that's so-so, 50-50. I mean, I personally have my 7200 set up on 10 hertz steps all the time, but sometimes I do 1 hertz. Okay, this is the programmable crystal from Hans. It's a little synthesizer chip, and there's a little tiny controller underneath. Now this whole board, I mean, well, there's 100 yen.
As always, his boards are huge.
Yeah, I know they are, aren't they? It's so hard to work with. But what it does, it actually has 3 outputs, and there's 30 memories, and you can program frequencies into each of those memories, obviously, and then with a BCD code, select which frequency you want. But so it's a programmable crystal. It's not a VF or a VFO or anything like that. The reason that actually it's a new product, and I just stumbled across it. But the reason I used it is because, for example, I said my IF was going to be 833. Well, that's just because Akihabara had a big box of them there, and I bought every one of them. Now, they may or may not work out. You know, it depends if I get a crystal filter, get them lined up in frequency close enough, I can possibly use them. But if at some point I wanted to go down to 4.5 megahertz or 9, then you would be, if you have a separate crystal BFO, you'd be stuck having to buy very, very expensive crystals to sit on the bandpass slot. In this thing, you can actually move it 1 cycle steps if you so desire. So again, it's a programmable crystal, and for the price. The only downside is that it's a synthesizer chip. And synthesizer chips put out square waves, not sine waves. The DDS puts out a digitized sine wave. So it's got little tiny steps in it, but it has spurs too. It has some spurious frequency outputs that are somewhat away from the primary one. These put out square waves, so you have to run them through a filter. You have to run them through a bandpass filter, a good bandpass filter, to make a decent sine wave. Otherwise, you're really going to have trash. But they're pretty good, I hope. See what happens. Now, here, after I got the DDS and built it, again, it's a kit, I put it on a test jig to see if it worked, and it does. So right now it's operating at around 12 megahertz in the B memory, and the RIT offset is set at 500 hertz. Obviously, I don't know if you can change that. That's manufacturer. I'd love to have my call there. You know, you order it, he says, write your call down. So I was expecting to get it with my call in it, but that wasn't to be. It is program. There are things you can program. You can do some programming with it, but basically it's just some, you know, external settings and things like that. I mean, you can't go in and really make any serious changes to his code. Now, The encoder sent,
Does his code, is it
it's proprietary, it's,
like a firmware you can
Yeah.
update and load it?
Yeah.
So you could maybe open it up in like a bin hex, I don't know.
well,
Search for
you
that.
know,
It's probably not encrypted.
I doubt if it's encrypted, but I thought about it, and the thing is that it would be easier to get an Arduino. In fact, the guy in Australia uses an Arduino and get his own program. He can put all his own features in it. And that's, if I was going to do this again or upgrade to a multiband, that's what I would do also. I wouldn't fool with, this is a PIC chip, so it's all assembler. Now, the Arduinos are in semi-C, C++, which I'm very much at home with. But assembler, it's been 30 years since I did any assembler. And that was our 8088s and 8080 Intel chips. And I don't think it could handle this. But the encoder sent is a mechanical encoder. It's a little tiny square guys. And it's got slop in the shaft. And the pulse rate is only about 25 pulses per revolution. But anyway, it's not what you would say is transceiver quality. So, this is what I got. Get a good encoder, an optical one. Now this is from the same company I bought the PA from, the RFPA, from Mini Labs in Australia, but it's a Chinese encoder. But it's for a CNC machine. So these are actually, it's ball bearing races on both ends of the shaft, and it does spin free. There's absolutely zero lateral movement to it. It is rock solid. In fact, it spins so free, you're all over the place. So the question is, when I first bought it, it has this 20 millimeter lip on it. And the mounting holes are here. They're a real pain in the butt. What am I going to do here? I wanted to recess it so that I get this below the front panel. And then when I was playing with it on the jig, I thought, well, you know, this thing turns too smooth. So I want to break it. Now, on the web, and iPhone EAC have some very elaborate braking schemes for their knobs, pressure fingers and all. But Elecraft and Tentec use a felt pad. And you won't believe how well it works. This is, I think it's about this thick. It's probably 3 or 4 millimeters thick. You buy it at well, the Optima or whatever else, Shimachu. Using this as one surface to break against, and the flat of the knob in here, and it increase the resistance just by setting the position of it. You can get it so tight that it's actually very stiff to move. And if you back it off a little bit, it's almost free turning. So it turns out, just look at the dome, I guess, it's super brake system. Anyway, so we got the encoders. Now, let's start to build the chassis. The box is about this big and about this deep, so it's not very big. But because it has a LCD in the front, and you have to mount the DDS, and there's ribbon cables that go between them. And I wanted extra shielding. I opted for a sub-panel that sits behind the front panel. Here's the front panel here, and then there's standoffs, and the sub-panel goes here. And then, this is the bottom view. I put a shield here on the bottom. This will become the power supply area. This is the transmit area, and the top is the receive area. we have already some basic shielding starting to look, appear, keeping the primary section separate. And as we go along, you probably say, well, this is really getting out of hand, because it kind of did. This is the front panel. I've got some holes in it. It's really a turkey to work with. So on 1 millimeter aluminum, and I would have preferred 2 millimeter. 1.5 to 2 millimeters is much easier to work with for front panels than 1 millimeter. It's just too thin. So when you're making square holes, it's hard to make them look good, and it's too easy to make a mistake. But take what you get. The cabinet itself is steel, so it's good and rigid. But the front and rear are 1 millimeters. The big point in these things, at least from my point of view, is to make it easy to use. You're going to play with this thing and play with it and turn dials, whatever. And you don't want to be catching your thumb or you're catching your finger on something, or finding yourself trying to tune this and go over here across and push buttons. You want everything very close. Therefore, the tuning is free of any additional controls, AF gain, and this is the DSP selectivity. So everything is real close. The buttons here are basically AV, split, break, and things of this nature. So they're actually very close. You can do it all with one hand. The other controls that we don't use very often are further over to the left. But, and I kind of jumped around. I mean, you kind of have to build it up in pieces, in stages. Because if you go too far in one direction, in one area, all of a sudden you find yourself having screws that are hidden. You can't get at them. Or you put something in front of something else and now you can't put any wires on it. I mean, it really gets crazy. So it had to come up in pieces. Considering the size of it, the front controls are basically, you're limited by space, what you can have on there. And so I put them on very early. The guy in Australia, he actually breadboarded everything first, and he built the hardware. And I'm kind of starting the other way around. I started on the hardware front, the outside hardware, support circuits, and then once everything's working there, then I'll go back into the electronics themselves. So there's a couple of ways of doing this. Anyway, I don't know if you can see this very good. This is the front panel on the back. Here's the hole for the S meter. Here's the encoder. It's quite large. It's probably about that big, not that big around. It's quite large. So it does take up some space. This is the LCD on the other side. And the LCD, boy, that thing was really a turkey to mount. Because the screws that come through have nuts. You come through here's the front panel, the LCD, and there's nuts or screws that go through and have nuts on them. They actually tie the LCD display right up tight, and then add some more nuts and spacers, round hex standoffs, so that I can get this plate mounted. This plate, basically, as we'll see, has one PC board on it. That will become the interface for the DDS, the encoder, the switches, and some stuff over here. It's basically an interface board, which is actually kind of, we'll get to see it next after this. On the sub panel to the rear, we're looking at the S meters over here, the encoders under here. This is the AF amp, and the DDS itself. The AF amp, I cheated. I just got something from Aki Albert. Excuse me. The reason is, for the size, you can't beat it. That thing runs 9 watts into 2 ohms. If you had a 2 ohm load, it running 9 watts. And the distortion is only 0.07% at half a watt. So it's a stereo amp. And I have an 8 ohm load on it, so it basically probably puts out 2.5, 3 watts maybe. And has its heat sink already on it. So small. So it's just an easy way out. Just because you're home brewing, you don't have to home brew everything. Now, again, the front panel is still, but I did get the DDS turned on. In this case, we're running 7 megahertz output. A couple of the status lamps that are switched from here. They're just sitting in the S-meter hole temporarily, but just to see what it looked like. And there's a couple of things that really kind of bothered me. Number one, the biggest one, was light leakage. This is the cheapy LCDs. And on the side, backlight is, so you can see it. On this side, they have a groove or an opening cut in the frame, and you can see the backlight here. It really looks cheapy to have the display and have the backlight. So I didn't know how I was going to take care of that, but I was bound and determined that that wasn't going to happen. But we'll have to wait and see as we go along here. Now, once I had the DDS is in here, so I had to start making holes for the modules. Now, a lot of times, QRP transceivers are one boards. Everything's on a single board. This one's not. This is, every module will be shielded in its own enclosure. This is very close to a military type construction. I mean, everything is shielded. There's high quality coax that will be connecting it, which from a fabrication point of view is really hard because I don't have drill presses, metal brakes, or shears. I simply have, look with Johan, the floor, a hacksaw, and files. All these with. Everything's cut by hand with a hacksaw, a nibbler, and filing. Lots of filing. I drilled my wife bats. Okay, so that hole now goes from the top to the bottom. This is the PA board. The empty, it's a bare, it's still bare. The PA board mounted. And the reason I had to do this early is because the heat sink has to attach, the transistors, power feds, have to attach to the heat sink. So it has to be placed right. And as luck would have it, it was recommended just fit. Just fit. And in fact, the fins are quite thin. And they're actually quite sharp. It's an extrusion that has simply been sliced and then they sell it. There's no finishing. So those corners are really, really kind of sharp. But I put these here, hoping to protect the heat sink to some extent. Unfortunately, the corners still hang out. But if somebody really gets the slam on the side, it'll take most of the hit, not the heat sink itself. But so the heat sink has got the PA's got its place. Now we are going to Okay, this is the same, well, it's a different picture, but it's the PA from the flip side. This is the transmit area. The power area. So the PA is accessible from the bottom. Well, this can't see, I guess, from the light, but the PA sits right here and with the center shielding. Now, I think if we've got a picture of this or not. Yeah, we got a picture. I started to add to the rear panel. We got a power connector. Power connector was hard for me because I didn't know what to buy. Actually, the screw-on, old-style Japanese equipment connector was really good. They used it like for a mic connector. It was really good. Antenna, earphones, speaker. This is a, what, 2.5 millimeter, 3 millimeter, 2.5 millimeter, I guess. Key input, key, push to talk, and send. So when you're sending, this will go low, and you can use it to control whatever. And this is what it looks like from the inside. All of some of the controls have changed. So there's not a lot of room to work with. The PA is going to sit from here on, and there's a shielding here, the receive area, the transmit area, and the power area. So considering the size of components, you really can't make it too miniature. I mean, you're stuck with what you got. I mean, you know, Icon, they make these little tiny things, and they fit this and they fit that. You don't really have too much choice. So anyway, we've got the power and the antenna finally mounted. Here I had nuts that hit each other, so I had to do some filing so that I could fit them in. That was very typical as I went along. Now, here we start the battleship building. This is the PA shielding on top. The guy in Australia said, asked me, kind of tongue in cheek, he said, "Did you use enough screws on it?" And add another 20 or 30, and the thing would sink. But after I looked at it, I had to agree, I kind of went overboard. These, on the outside here, these are self-tapping screws, so you can take this off. In fact, yeah, you can take this off, this shield will stand alone because it's fastened at the bottom, which has connections, the wiring connections in. On the bottom, similar construction. These are 2 holes to adjust the PI bias. PA inputs here, outputs up here on top. So yeah, I kind of went overboard. Looks good though. I don't think I'm going to have much emissions from it. Here's another overboard. Even when I worked on military equipment ages ago, we'll always use bypass feed through capacitors. From compartment to compartment, you know, one work shield area to another is always through. So as I've done before, everything that has going into the various compartments. Let's see, this is the power. This is receive, so these are the receive power feed-throughs. This is the transmit area, so these are the transmit power feed-throughs. This is the front panel, and there are a few there for some voltages and some switching. And see in the power area, I finally added one board. This is a power on relay and a fuse. This is quite interesting in that you can reverse the power connections and there will be no damage. 0. you know, you get plus and minus, and this particularly would happen in the field, somebody hook it up and get the suckers reversed. The minute it's reversed, the front panel will indicate a red LED saying it's reversed. I push the power switch will not work. This power relay will not operate reversed. So it is totally protected from a setting mistake, which, so. Now, as you may expect, with all these shielding, we had to get wires in and out. This is on the right side, front panels here. Power amplifier, AF amplifier would sit here. This is a square hole I made to bring cabling from the front panel. And that was rather nasty to make. This one was even worse. This is I think it's 5 millimeters by 21 millimeter square hole that these little miniature headers fit through. And it's soldered on the back of the PC board and then held with a couple of screws so that you have 16 pins to bring front panel switching stuff, mode switching, things like that, into the transmit area. This is into the receive area. So, well, it's pretty good yet. I mean, I haven't still got a little bit of room to maneuver. In fact, this is that 16-pin connector. This is where it attaches on the rear, and right adjacent to that is a board. Shows one board. I may use two boards. This is where the QSK, you know, the CW switching, mode switching, and all that kind of stuff will be done right here. So it's very short jump into here, and then the switching signals will go into the power area and into the receive area. So let's see what we got next. Okay, now, as we saw, we had the DDS mounted here at the board. Here's the AF amp. Now I have to shield the DDS. And that was really exercise in stress. Bending a right angle aluminum, two pieces, identical, was really difficult. I went through probably 3 or 4 tries before I got two that actually matched, top and bottom. And they're held on by angle brackets on the front panel. And then, as before, aluminum plates. Here's one here, sit here, and on the other side. So that is completely buttoned up also. And there's only that 5 millimeter slot here at the top where the ribbon cables go out to the LCD. Other than that, it's tight. And again, feed through capacitor. Unfortunately, there's a board that fits in here, and that screw is not accessible. So we have to take all kinds of stuff apart just to get one screw. The other problem I run into is it's not that deep, really, when you get the secondary panel on that. So the distance between here and here, best it's only about this much. And I didn't have a screwdriver to fit down here. And when I went and bought a short screwdriver, the handle was too big and it set at an angle. So I had to double up a time trying to get those screws out, but I got a little ratchet thing that it seems to work. Okay, now basically here, we've got all the holes, and I put some of the controls on it. And this is indicate, I don't know, you guys probably don't have this particular scope. It's a Chinese DSO. But I just put it side by side so you can see approximate size comparison. I bought this specifically just for this rig. But it's crazy. I mean, it's fun. with shipping, about 42,000 maybe, from Hentech. And apparently there are presently price wars going on between 2 or 3 Japanese companies, Tektronix and a few others, for low-end DSOs. As a result, the price is ridiculous. This thing looks kind of like a lunchbox, but has a 200 megahertz bandwidth. It's a 1 gigahertz sample rate. And, you know, all the mathematics and everything else. So for that kind of price, you know, it's kind of hard to beat. Without it, you know, I couldn't really go, I wouldn't have been tempted this. But let's see what we've got. Now, front panel lettering. Now we come to the bugaboo of the home brewer. How do you make a front panel look presentable? I mean, anything from magic markers to Dymo labels or decals. There's been a lot of, you know, a lot of different ways. Myself, I don't put labels on my small stuff because I'm the one that uses it. I know what the switch is, so I don't want to make it look ugly. Well, on a transceiver, I couldn't do it. I had to put, you know, make it look good. So this is a recommendation of the guy in Australia. It's actually, he uses different software. I use a simple C program, and I type in my locations and then compile it and print it out on PostScript. And then it's laminated. His lamination, I think it uses 200 micron lamination, but the Seiseki, the Bungogia store, they only have 100 micron. It's a little bit thinner. But that's what it is, and then you punch it with punches, which is an interesting exercise in itself. Now I'm going to pass this around. This is not the one that's actually being used, but this is a one that's been made up, and this is what it looks like. This is full size, by the way, the front panel. So you basically print it out on photo paper, high quality photo paper, or if you don't want it too shiny, use a semi-matte paper and then laminate it and then cut it and punch it and hope for the best. The laminations are cheap because of the size of the front panel. I could fit 2 in an A4 size. And for an A4 lamination 1 was 300 yen. So for 150 yen, I get 2 front panels laminated, which is good because I went up there 3 times. But it works out good. The real pinch is getting holes to line up. I mean, you have to be dead on. And I found out a couple of things when I did this that, well, again, I went through, actually spent 2 days and probably made 40, 50 different printings on regular paper, trying to get these silly holes to line up. And then it dawned on me later that I was using standard PPC paper for my test. And the stupid stuff would bubble and stretch and move. So once I started using a heavier paper, then I could nail it down a lot faster. But there's some interesting problems that occur. You see the type of scale I had here with the traditional circle and the ticks. If you put a knob in that thing, and that's not dead center square, perfect, the eye will pick it up. Because the skirt of the knob will show you how far you've drifted. And, you'd be off center. And anybody that looks at it will pick it up immediately. So you can be off about 0.5 millimeter, and it's quite obvious. So on the real one, which we'll see in a minute or so, or near the end, I took away the half circle and just brought the ticks down into the skirt of the knob. So they were still there without numbers, but there was nothing for the eye to reference. There was nothing to say how far off or how, because with simple tick marks, hairlines hanging out here, it can be off 1 millimeter and the eye would never know it. With this silly circle, it was bad news. The other thing that caused me never-ending problems, there was 3 LEDs, there's 1, 2, 3, and then 2 over here. And they're on opposite sides of the page, and they have to line up dead on anyway, because those LEDs just poke their way through the lamination. And if you slipped a bit, they just won't line up. With the knobs, the nut will cover it. If it's off plus or minus a bit, the nut will cover it. It's no big problem. Same with the switches. LEDs, they're a real big problem. You have to be dead on, which was a bit stressful. Okay, here's the one. Now this is the second one. And you can see the difference in the first. This circle, these circles here, the tick marks, the numbering, they're gone. The reason is the numbering was getting in the way, and then it's no use anyway. So again, the tick marks are moving so that they go under the skirts. And I removed them here because I think it's a 24 detent encoder. So I actually have one line for each detent. So here's, from a feature point of view, here's what we're looking at. RF gain, IF gain, and AF gain. I have all. This is a noise blanker level. If the switch goes up, noise blanker's on. Now I ran out of room, so when you push the switch down, it goes into tune position. So I just kind of cheated and double duty on a switch. Now here's where it gets a little bit strange, probably for sideband, but not for CW. AGC is on, but I'm using 2 types of AGC, both RF and AF. The RF AGC runs the attack time, and the AF AGC runs the decay time. And you can set them both fast and slow individually. The fast and slow attack and decay on the AGC, which you probably no one's ever seen before. Mode switch, basically immediate CW only, so CW reverse, flip the carrier on the other side. Attenuator, and again the AF filter, and the AF filter reset. There's 6 little push switches here. So this is memory up, memory down, split, A to B, A/B, step, and semi break-in. I only operate semi break-in, so that's what I use. No full break-in. Wall. And these are the status for break, split, and when you're transmitting, the little red LED will come on. So that's the front panel. Now, you'll notice, maybe, it's hard to see here, these are not normal screws. Black hex head screws. I hate it when you have LCDs with little silver screws in the corner. It looks so homebrewy. So I decided, I couldn't escape it. I needed the screws. I better give them some character. So they're the black hex type screws. And it doesn't look bad, actually. So now we're going to build a power supply. I added here's the shielding between the transmitter and the receiver. This is about a 4 millimeter thick aluminum bar that's and screwed in to be used as the heat sink for the regulators. Because, you know, I've got one heat sink here. What's it for? Can't remember. Oh, I think this is, it's either 5 or 8 volts. I think it's 5 volts, which will run some logic and possibly some relays. And then here, low voltage dropout regulator. In other words, normally on these 3-terminal regulators, they need about 3 volts of overhead. If you ran, or 2.5 volts, but if you ran 13 volts in, you basically regulating down to 10 volts, you're right on the edge. So if you go, if 13 volts drops to say 11 or something else, like in a field day situation, basically it would just stop working. These are low dropout. They only require half a volt overhead. So I can actually run this down about 11 volts without a problem. These two guys here are FET switches. These basically do the transmit receive changes. There's voltages that are called VRT, which is voltage operates irrespective of what you're doing. There's a voltage R, which is only on for receive, and a voltage VT, which is only on for transmit. And basically the 10 volts is switched here with the logic signal, and you can actually switch these FETs very fast, and it works pretty neat. So that's what, in essence, what's going to happen is that these will actually control the transmit-receive operation in its entirety. Man, we'll have to get. Okay, now, as usual, I ran out of room. Area underneath basically is one buffer amp and some filters, so I got tons of room. Receiver, I ran out of room in a hurry. Had to add a secondary chassis here. So what it basically amounts to is I've got 30 millimeters of clearance here, 30 millimeters of clearance here that modules have to fit into. So they'll start at the RF amp and come down to the mixer, crystal filters, etc. End up at the product detector, and then the audio comes back up here. This is the DDS board, and there's a buffer that we'll see pretty quick, I think. We got one more thing here. The board here sits in the back, relay and the DDS reset. Interestingly enough, when a DDS receives power, it has to boot up to you. So when it's booting up, there's no output, or it's really off the wall. It's strange. So during the boot time, which is about a second to a second and a half, you don't want audio coming out, blowing off the chair of just strange noises. So there's a mute circuit that is normally used during transmit anyway. What I do is I delay the 5 volts to that mute. It's actually an optical FET switch, so it's LED running a pair of FETs that is doing the switching. So if the LED's on, audio is passing. If it's off, then there's no audio. So if I delay the power to the LED, then basically the receiver stays in a mute condition for the first 2 seconds. When you first power it up, it'll stay mute for the first 2 seconds, or you can adjust it. By playing with the pot, you can go from a second all the way up to almost 3 seconds. And then the little reset switch is on the back of the panel, and there's a relay, extra relay on here for the send to the outside world. I had to use a relay because I don't know what's going to be out there. I couldn't use a transistor. Now, we're back to, well, the power supply is now wired. And this is the interface board that sits behind the LCD with all its plugs. And it's got single shot latches so that if you push the switch, you'll actually have a bistable latch. So you can turn something on, turn something off. It's kind of neat because I had to do it. Now, the DDS is here, and we're going to run it into a buffer and a splitter. And that's the box. It's only 35 millimeters on the side. It's 20 some odd millimeters high. And you can see the size as compared to RCA phono jacks. The phono jacks are huge. But there has to be 2 transistors and a pair of toroids in there to do a little bit of splitting. My feed through, I couldn't fit it, so I had to solder the sucker on the side. Anyway, and it's mounted right up here. So the DDS comes out of here, plop into here, splits 2 off, one to transmit, one to receive. And I haven't built it yet, but it took some thinking on how to build these little boards. Basically, it's there's a 15, yeah, I guess, no, maybe it's 12 millimeter stud here that screws into a 6 millimeter studs in the bottom. The studs in the bottom are actually soldered to the board. And when you make them, basically cut the bottom, cut the top, and then drill through both simultaneously. So they're lined up. Then, we've got holes in the bottom now, of course. You put the studs, little studs, screw them in, and solder, and then remove the screws. So now you put your board in, and these studs on top, and then finally is the top of the box itself. Now, I haven't done it here, but I have some copper tape that's about this wide. These are single-sided boards, and I really will want a seal here, RF seal. So I can put a copper tape here and then clamp the board onto the copper. It's copper on this side, phenolic on that side. Interestingly enough, TIARA doesn't sell anymore double-sided board. Double-sided piece. Nope, can't find it anywhere. Talk to, especially now. No, and I spent 1 or 2 Saturdays looking. I finally just gave up and asked why. First thing is, double-sided PC board has become very expensive. Secondly, the number of do-it-yourself people going to TIARA, buying it, have decreased dramatically. So the stores, it's not profitable for them to carry that type of board anymore. Now the guy asked me, he said, "Do you want me to order it special for you?" I said, "No." So my boxes are going to be single-sided. But you know, it's just the way things go. It's hard to buy variable capacitors too. Here's a rat's nest. I'm wiring the front panel. And this was, I went through about 3 or 4 cups of coffee doing this. I had wire all over the place. Had no idea what the hell I was doing. You'll see, this is where the S meter area is. Here's the encoder. You'll see the wiring coming off. There's a reason for it in that when the front panel's mounted and you get your wiring on there, you still are going to have to and I already have to get in here and fix something, change something. So if you've got all kinds of wiring in here, how do you open it? Now, this cabling all comes off to one side, so I can actually open the front up more than 90 degrees and the cabling just turns with it. So there's no cabling going direct. It's all clumped in one spot so that you can move it, open it up. Back's the same way. And I think, what do we have here? Okay, this is some more cabling stuff. You can see the cabling coming up through the square hole, and the routing gets a little bit sticky. Anyway, I got this far, so I could decide, well, I'm going to put some power on my S meter. Yeah. Well, it's there. It looks orange. It looks like an orange. There's supposed to be yellow LEDs. I'm really having trouble here. The reason is that this meter face is opaque. It's aluminized paper or plastic or something. Anyway, light does not shine through it. So you cannot put light behind and show the meter face. The lights have to come in from the side. And when they do, if they're too bright, typical of plastic as a plastic box, the edge will transmit light. So you get very bright light around the plastic edge and still poor illumination on the meter itself. I'm still fighting that. I may just give up. Well, it's at some point it's going to be more trouble than it's worth. Okay, here basically is the front panel wiring. Now, all the wiring, it's all been tidied down now. As you can see, runs here. So I can open this up without a problem. The rear panel, all the rear panel wiring, you can see it loop here. That loops so that you can open up the rear panel, lay it down, and get at the PA, and no problems. There's no wiring that goes direct. It goes through the cable bundle only. But let's see, we're getting close to the end here. Okay, now I decided to add some eye candy. So I added a plastic bezel here. And I knew I wanted to do it, but I just was super hesitant because cutting meat and acrylic, for some reason, don't get along very well. Either I crack it, or I scratch it, or it just turns out cattywampus. For some reason, and I don't know why, I'm cutting it by hacksaw and filing it, and I had some sandpaper all the way down to 10,000 grit, which is pretty fine. Actually got a nice shine on the edge. The biggest problem was getting originally the LCD was out about 1.5 millimeters that extended past the front panel originally. But when you put this on, you have to have it flush. So I played around with washers and all this stuff for a good part of the day, and I finally had it flush, and I could put the plastic on. And I thought, wow, this is great. So I get everything down, finished, and I turned around and looked at it, and I had these streaks that are around the screw area, these funny streaks, like contact streaks. You know what happens if you take, for example, a piece of glass in a jar of water, you squash it. The surface tension, you can see it. What apparently is happening here, between the laminate and the acrylic, there was enough surface tension or surface whatever that it would stick. And you could see an outline where it was stuck, really tight. And of course it happened with the screw holes. So, oh, this is bad. So I took it all apart and had to add, what is it, 0.25 millimeter thick washers standard washer, but they're only 0.2 millimeters approximately behind this. So doing that, then I had to move the LCD out 0.2 millimeters on all four corners. So this is actually relieved from the front panel by 0.2 millimeters. And no problem, looks good. And another kind of a strange issue with the laminate, you can use double back tape, put it on, but you only get one shot. The double back tape is sitting there and that's it. So initially, on the first try, I didn't use any tape. And here, particularly here, I was getting it was pulling away from the panel because there's not enough laminate surface area. It was too thin. So next try, I got double back tape here, across here, down here, a little bit. There's nothing here. It's all, they were held on by the nuts. But in the weak areas, the thin areas, there's double back tape to hold the laminate really tight to the front panel. So we've got the bezel on. Here's what it looks like. Get the meter's going, DDS is running, AF amp is running. And that's what it basically looked like when it's finished, other than the color here. Didn't push any switches, so these guys aren't running, but they do work fine. PA, the audio amp, I wired it up and tried it. First time I wired it backwards, not backwards, but on the rear panel, there was 3 millimeter jacks for speaker and bigger ones for the 6 millimeter for the earphones. But it's a stereo jack. So I thought, well, I'll wire this up so the tip and the ring are shorted together. So if somebody plugs in a stereo phone, they'll hear both ears. Well, that's fine as far as it goes. What is bad is the reverse. If somebody plugs a mono plug into it, there's no ring, so the AF output goes right to ground. And I had the speaker plugged in and nothing was coming out. I left it. I burned my hand, I've still got marks, off the heatsink, just super hot. Uh-oh, I made a mistake. So then I finally figured out what I did, and I fixed it. And I tried it, and I can turn the gain all the way up, and there's no hissing, there's no shh, there's no white noise, 0. And then I went and pushed all the buttons here and played around with the DDS to see if I was getting any noise or any popping, any digital noise in there. No digital noise. So far, good to go. But the guy in Australia pointed out that, and there was a couple of other articles that pointed out the same. In fact, there was one in a QST a few months ago. A lot of people overlook the audio amps. They marginalize them. What they're rated, say for example, 2 watts, 10% distortion. And they're very noisy. Reduce the noise, the makers put wave shaping on it. We're going to cut this off at 3 kilohertz, at 3.5 kilohertz. And we're going to cut the bottom off at about 200 hertz. So I'm just trying to cut the noise. So you should have an AF amp with lots of overhead. Just take whatever you shove at it, low distortion, and your signal will sound tremendously different. I mean, just tremendously different. Well, of course, I have yet to see if I will or not, but I mean, theoretically. And basically, now I have to be able to receive and transmit stuff. Now, most of the stuff you know, for example, polarity stuff, that's done. This is done. Low pass filters, I have the parts. PA, I have the parts. We got to do this. Basically, I have all the parts here. Synthesizer is actually finished. DSP filters, no problem. This is finished. Side tone works. Power delay works. Some of the big stuff, you know, I still have to build them, but I still have to try and sort out the CW key, break in, the timing sequence. You know, when you go from transmit to receive, the timing of various states has to change in the proper sequence, otherwise you have problems and you don't want to burn up the PA. But that's it. It's hot in here and I'm sure everyone's going to sleep. I threw it together yesterday. I thought you may be interested. I mean, you don't see a lot of homebrew anymore. I mean, this is going to be a long-term project. I mean, basically, I've been working on it for what, 6-7 months already.
I have something on my basically the receiver is or transceiver is in case of receiver OV1 or 1V1 or something like that, a very simple receiver works. The probably say long time ago, but not like auto-dyne.
I know auto-dyne. What an auto-dyne is.
Auto-dyne or something like that. Very simple receiver is simple is best, I believe, but it have to be careful for a lot of frequencies stable. But now in modern times, the digital technology has advanced, so that will be very helping for, as you mentioned, the DDS.
Well,
something like that, a very stable VF.
Well, the point is that the issue here is that if you have ever heard a Drake receiver, or yeah, particularly Drake, they sound super clean. There's no noise. CW just sounds beautiful. There's no digitization in it. You know, there's no DSP, there's no digital this, there's no digital that. It's just pure analog. Single conversion. Therefore, every time you go through one of these mixers, you pick up noise and spurious. You pick up intermodulation distortion, IMD. So in this case, there are really, there's no, what should I say? There's no diode switching here. It's all relay, because diodes introduce distortion.
You mean no cosmic noise generation?
They'll actually have mixing products. Diodes will cause mixing products, and you will pick up IMD distortion using diode switches. So everything here is relay switched. But there's only one relay. There's only, you know, it's a single conversion, so it is super quiet. There are the number of active components. We've got 2 devices here active, one here, one here, one here, and then the DSP filter, which is the chip. So that number of active devices is really quite minimal. But there's 30 decibels of gain here. There's gain here, there's 40 decibels of gain in this IF amp. You have more than enough gain. The AGC basically can handle over 100 decibels of change. So today's receivers, or transceivers, you'll find them all band receiver. The transmit, maybe it's just ham bands, but the receiver goes everywhere. So they're running, for the most part, triple conversion. First conversion is going to be about 45 to 70 megahertz. So they can get away from the images. Then they'll go down to maybe 8, 9, 10 megahertz, and then usually wind up at 455. Because that's for the filters, they're easy to get a hold of. Like the guy in Australia said, for the home brew person, making a 70 megahertz high performance RF amp and mixer is really, really difficult. And it's just, he said there's no even reason to try it, because filters are hard to make, the active devices are hard to control, oscillations and all kinds of crazy stuff. He said it's just too much work. Now, the guy in Australia's case, he's making a full coverage ham band 160 through 6 transceiver, and he's using a 9 megahertz filter in his. Single conversion, basically almost the same makeup, the same devices. But in his case, he's using a synthesizer being driven by an Arduino, and I'm using the DDS. He's using individual crystals for the VFO, and I'm using the synthesizer. His is SSB2 and FM, so he doesn't have the DSP filter. And basically, he's got the same PA. He bought it after I did, but he also has a 200 watt PA that he will transistorized PA that he's going to use later. But he belongs to a club down there that full of homebrew people, and they're going to use it for instruction how to do. And this is the easiest approach for a guy with average test equipment, with average skills, to get something that works. It works pretty good. So that was the reason it was chosen. I mean, you know, direct conversion receivers have their troubles, but they're very, very quiet. Direct conversion types, but some people like them for a little homebrew. Anyway, any other questions? Everybody's still awake.
I suppose you've been very enjoying to joining construction do the whole.
Yeah.
But after that, and they goes to the finally small problems to find out. After that.
Well, basically, yeah, granted, I mean, that was one reason that I've done all the outside stuff, like power supply, the AF stuff, get that out of the way, get that working. And then the next step is the product detector. Now, this is already built, and I have to fabricate a low-pass filter or a band-pass filter here, because this is square away. Or, to test it, I can take the DDS output and run right straight in here. Put an antenna here, and you have a direct conversion receiver. And you can try it. I mean, it'll work. So, once that's done, AFM. AFM is one SND device. It's quite simple. Crystal filters, they're going to take some time. Mixer, it's brother to this. They're the same, slightly different components, but basically the same. The RF amp, it's this is the SMD, this is standard chip. Attenuator is no problem. And so, I mean, it's simple enough, theoretically, and I don't create big problems that I can't solve. Doing it a step at a time, hopefully. The AGC has got a lot of parts. That's going to be tricky, because the AGC voltage here is not the same as here. It operates differently. So the dynamic loop is a little hard to control. But we'll see what happens. I've gotten this far, I'm not going to stop. I've got too much money now.
Last question. How did you find the time to construction?
Well, I still
with your wife.
Well, the wife's not the problem. I still work 7 days or 5 days a week, 40 hours a week. I still work every day of the week for the UK.
You have only a room?
Well, I got a 6 dummy room that I have 5 PCs in, towers, that runs that I do my work on, and they talk to 3 more machines in the UK.
What do you do?
Well, 20 years ago, software development, programming, but now basically write test cases and test software that's been written in the UK. I'm at 74 now. I'm past the time. I don't want to program anymore unless it's for my own personal enjoyment. I'm very comfortable with the C language. I can get by in C++. So that's not a problem. But I did hardware before I ever did software. I started out in hardware tubes, maybe on vacuum tubes. And I worked in the test and measurement industry, hardware, DSOs, distortion analyzers, function generators, stuff like this, 40 years ago. So I did that first, and I was a ham man. And then, because times changed and I couldn't see the parts anymore, I changed the software. And then I started programming. And I did that, this is 19, published my first article in 85, maybe? Actually, no, it was earlier. Yeah, about 1985 was my first. I had a couple of products that were published in a software magazine here. And now I'm back to hardware again, but the world has changed. There's no more heaters, there's no more screens, there's no more plates. It's all this little tiny stuff where you got to get out magnifying glasses to see the lids.
You can still have some code in there written in COBOL or something.
I've never played with COBOL. I worked with Pascal and I worked with Lisp, but COBOL was, there's still a lot of COBOL used in Japan. Most of the heavy industries, particularly the steel and the petroleum industries, still use COBOL, and they've used it for 30 years.
Don't touch it, still works.
And well, the problem is a lot of it doesn't work. But everybody that could program in COBOL is dead. So that's very hard to find COBOL programs. Remember the big the year 2000 hype? The world was going to cease. Our software world was going to end in the year 2000 because of the rollover bugs. They were trying to dig out COBOL programmers all over the place, and these guys would be coming in their wheelchairs and stuff. And that was really a kick. But
So with all of this hardware, what does it end up weighing? Have you weighed it?
well, that's another touchy subject.
I do recall him saying it was supposed to be lighter.
Yeah, exactly.
That's
the motivation.
The last time I weighed it, I haven't done it quite a while, kilograms. And I still had a lot of aluminum to add, and a lot of stuff has to go in. Probably committed over about 3.5 kilograms. I think the guy in Australia did a bad time. He says, I thought this was portable. Yeah, I did too. He said, what are you going to portable? You know, what are you going to do? You pull it on a little red wagon? Or you give you a real bad time. Monster. I mean, it's a huge thing. It's got a big base and he can. He's got a filter that I would really love to have. It's from KVG in Germany. 30 years ago, the KVG crystal filters were the epitome of crystal filters. I mean, that's like very comparable to the so-called Collins mechanical filter, for 455. These things are very expensive, very, very good. And he has a couple of them that he's using. This crystal filter is a make or break for a CW receiver. It's a make or break. And it's an interesting thing about it. When you think about a crystal filter, you think, oh, it's going to look like this. It's going to be flat on the top. And which is some of the hardest filters to make. This is true. But on CW, this is really bad news. Really bad news. Because what happens is there's a time delay going through the filter. And the time delay of this type of a filter, a very sharp filter, is actually like this. Longest delay around the edges. And if you turn up the selectivity on the filter, now, not on a DSP filter, but well, DSPs will do it too, but a crystal filter, and it'll start to ring, the ringing. So if you get noise or if you get a fast CW, you can hear the ringing on the edges. You're familiar with that? That's due to this time delay through here. The time delay will emphasize this type of, well, it's ringing. So for a CW filter, they have what they call a Gaussian filter. And it's actually, looks like this. And pure Gaussian is quite slow, and after 6 decibels, it will change. It'll change the slope down about like this. But, and the time delay actually slips off. It's not the same. So there's no ringing. And I've heard YouTube videos of these filters, one against the other, and it's unbelievable. There is no ringing. If you do a correct Gaussian type CW filter, there is no ringing, even at 300 hertz of width. So that's what I got to make here. And unfortunately, all the calculators and, plug in the numbers on the web are all for these very sharp filters. So I'm still pondering what to do here, but that's going to be the big thing to make or break this is going to be the curve of the filter, whether it sounds good or not. And I'm going to set this probably about 600 to 700 hertz, because that's what I operate at all the time. This guy goes from 3 kilohertz width down to, what is it? To 100 hertz, maybe, like about 100 hertz in width in audio. And that's got 70 decibel steps on it, very square. So hopefully it'll work out. Again, the DDS I can play with, you can change the offset if you want to. The programmable crystal, if I don't like the IF, I can change it, set it up for something else. The only thing is there's simple toroids in here. There's no little IF cans and all this other garbage. So it's really very simple. You can go from down to 5 or 4 megahertz without any trouble at all. It'd take about a day to set it up, but that's wouldn't be that difficult. Theoretically, it's not really theoretical. Anyway, end of story.
Thank you.
Yeah, well, it was.
Good.
That's still pretty big, but.
Prep and finish it, so you can bring it in.
Yeah, I've taken it before I did the front panel wiring on.
Since it's portable, you can bring it here.
Well, it is. It'll fit in here. Before I had the front panel wiring on, it looked like a spider web or an octopus. The other club I belonged to, all Japanese clubs, and Chu, and took the covers off and passed it around. There's 3 or 4 guys here that are really long time dyed-in-the-wool home brewers, and they really enjoyed it. To see the metal work and all this kind of stuff. And I haven't taken it recently because it's a spaghetti factory and it's just too hard to handle. But when it's finished, yeah, I can wrap it up in air cap. It's not a problem. It'll actually fit in here. I mean, my back feels like a break. I mean, physically it'll fit. But it's probably pretty close to the another 300 or 400 grams maybe. Maybe. All the metal work's done. That was the big stuff.
When do you estimate the completion date?
Well, right now, after working every day, I work Saturdays and Sundays on it, and sometimes in the evening. This is a picture before the bezel, and it's got the green case on it. It's actually a little clearer than probably you saw there. Interesting that the front color is almost identical to the British Commonwealth or the Japanese marine equipment, shipboard equipment. The color is almost dead on. The case obviously looks like adhesive, very, very green, but the panel color itself is quite close to the marine Raycal or Marconi set.
Looks nice.
Yeah, I'm really pleased with, and the bezel really makes it stand out, and the plastic, very pleased so far.
And then how do we order these?
Well, that's a whole different story. It's, you know, again, the biggest problem is the metal work. I mean,
Yeah.
I don't have a place to do it quickly. I mean, I don't have a shear, I don't have a drill press. I mean, I got simple hand drilling.
Just,
To cut all the aluminum, all the shielding, and then file it down so it fits right. And the thing is, these guys in shoe club, they are super critical. I mean, I bring it in and the guy says, look, you got a gap here over here. Look at that. And on the shielding with the two pieces, he says, I can catch my fingernail on that. Just drive me up a wall. I really have to spend a lot of extra time to make it almost as good as I can. So it doesn't look sloppy. But with most of the metal work done now, it's basically electronic stuff, so probably fall maybe. You know, depends on how much time I get to work with it.
before Ham Fair?
Oh, no. Ham Fair, you have to be 2 months, finished 2 months before Ham Fair to make an entry. So this year I couldn't do it, next year I can do a Ham Fair, but not this year.
実はちょっと僕マシンセンターが簡単なルーターが
Yeah, it's,
やだんで
ルーターから削るやつ。
そう。ほんでルートでこうやらできるね。
yeah, the filing and the cutting drove my wife crazy.
図で見て
Especially if you catch the file the wrong way on 1 millimeter aluminum.
10万円ぐらいで買えそうなんですよ。
Squeeze. You have to do that?